since we first met, and we first met as members of EVONET when I was invited to join that very successful initiative that shaped the whole European community in evolutionary computation, and especially it left us as an inheritance, an event which is now called EvoStar, which is something very something in common with WIVACE, since it's been mainly a volunteering effort to keep the community going by the whole community in the following 25, 26 years up to now. And actually, EvoStar is run by Species, which is now an association, but the association was created just to back up EvoStar economically. And so I think the same friendly environment that we can find in EvoStar is the same as we can find here. And so I was really happy to propose Wolfgang as an invited speaker for this year. From the more common viewpoint, scientific viewpoint, of course, Wolfgang has done much, very, very much for the EC community, for which I have known it for many times, for a long time, since I found out he had many other interests. And so I would say, especially I would say that if John Kosa is considered universally the father of GP, Wolfgang is at least the wise and old uncle of GP. And so I'm, from my viewpoint, it's quite interesting to hear what he's going to say about artificial chemistries, because I don't know that facet of Wolfgang's activity, and so it will be, for me, something like getting to know about the secret life of Wolfgang today. So I invite Wolfgang here.
Thank you very much. Yes, thank you, Stefano. Is this working? Yeah, perfect. Thank you very much, Stefano, Roberto, Francesco, Marco, who arrived, and everybody here for attending and for inviting me to this very nice location. Venice is really impressive. I was here last in 1982 in winter. It was cold and I was not very comfortable at the time, I remember. So this is a much better season to visit. Yes, and much to the surprise of Stefano, who promoted my name, I talk about something that has nothing to do with genetic programming. Although maybe at the end people will see. Yeah, thank you. We'll see that there is a slight relation between artificial chemistries and genetic algorithms or evolutionary computing in general. Okay, let me go in. Let me talk a bit about something that has concerned me for a long time, namely the problem of emergence. That's, of course, something you have talked about here as well. And I find it just very fascinating. How do new things come into the world? What is it that makes things that have parts of things come together to wholes? And what is behind organizations of systems? So this is, I think, a core problem, and I don't think we have at this moment already the formal tools to discuss this or have a good handle on it in mathematics. With the advent of computers, there's a new possible method approaching this. Advent is, it's happened 50 years ago, 60 years ago, but I still think there's a lot to explore, maybe using the computer to elucidate this idea of novelty, innovation. And after that, so this is a bit more philosophical, soft intro, and then I will talk about artificial chemistry, the ideas behind it, principles. I will show you one AC in action. That's an old one that I have developed myself a long time ago, but it's useful to understand the concepts, which are really easy. And then I will comment on how it relates to artificial life, give you a few examples of the tools or the methods that we can use to play with artificial chemistries, talk about formalities of organizations, and then hopefully at the end, I hope I have time to do this, to talk about a social economic model that I have studied in the last 3 years during the pandemic, actually, where I thought I wanted to come back to this since, I don't know, 15 years, where I use an artificial chemistry to look into inequality in society. Okay, so there's a book on artificial chemistries. It's from 2015, so already 8 years ago, published by MIT Press. My collaborator Lydia Yamamoto and I wrote this. It's the first book on artificial chemistries. If you are interested in the topic, I recommend you take a look at that. It should be online available as well. The problem of emergence. The universe did emerge, didn't it? We know about the early stages of the universe, while the Big Bang itself is under heavy discussion among physicists, whether it really happened and what happened before. If there was a before, of course, time might have started there. What is clear is that after some time, the so-called dark ages, suddenly atoms showed up on the scene in the universe, and after that, stars and galaxies and all these structures, larger structures that we have today. There were a moment at which no atoms were there, and then suddenly the first atom appeared. So something new came into the world at that moment. And it happened repeatedly in the history of the universe that new things came into being. Since about 10 years, we know that the mass of the elementary particles is an emergent property. It's produced by the interaction of massless particles, the so-called Higgs bosons. So even at this very fundamental level, apparently emergence plays a role. And by emergence, I mean new qualities that come into being through the interaction of things, and in this case, Higgs bosons. And so maybe our entire universe is based on the phenomenon of emergence, and we just have not yet a full grasp of that with our methods of formal methods of mathematics to make predictions about that or to understand it fully. Another example is, here is the periodic table of elements, and it continues to get filled with new elements, and the pink elements here on the right side are elements that have been produced perhaps for the first time in the universe about 10, 15, 20 years ago by humans in accelerators that pushed very heavily atoms together and produced new elements that perhaps never before in the universe existed. They might not be very stable, but they are new elements. New elements. And they got new names. so first of all, they had these standard names, and then they became really established with real names. So we have this, something new comes. We have repeated examples of that, even on a very fundamental level. We also have something else, and that is that it seems that nature is organized hierarchically. Here's a sort of a walkout from the Earth to the observable universe, and the Earth is part of the solar system, is part of a solar interstellar neighborhood, the galaxy and a group of galaxies, the super cluster and so on until we come to the largest scale structure. But even if we look at the biological organization, it is one that is hierarchical from the DNA, which is part of the cell, and then just jumping to the end, which is part of a biosphere here on Earth. So all of this is structured in layers, or is that just our idea about it? Is it just in the eyes of us as the behavior, as the observer, that we perceive it as a hierarchy? Maybe it's only an approximate hierarchy, not a full formal hierarchy. I leave you with that question. Yeah, there are these mysteries. How does something become a whole or a unity that can be perceived clearly as one thing and might subsequently influence its parts or other parts of a lower level? So how does something new appear, which a whole is something new at some point? And by the way, what does it mean to be new? I have 3 examples here from molecular biology, which I think are 2 different classes of novelty. The first one, a point mutation, it's just a little variation on, let's say, a gene. The second one, a gene duplication, where you take a full gene and copy it to another place, and maybe it over time assumes a new function, a new gene. That's a more serious kind of novelty. And then finally, a gene duplication. For example, we know that eukaryotes came about by genome duplication. So there's a whole new world opens up when you do this kind of thing. And we think that, other people have thought about this too in the context of creativity. There are different orders of novelty. Variation is the simplest, smallest. And then we have what we called in our conceptualization innovation, which is, let's say, the new gene type of thing. And then there is a much larger change, that's structural change, that could be called and has been called by Shatmari a major transition. You can also call it a transformation. We have written a paper about novelty in 2016 where we sort of discuss what types of novelty exist and how can we try to approach handling them. Okay, emergence. It's a philosophically loaded term, as you know. Aristotle, and I have thoughts here that certainly draw a lot from Stu Kaufman. Aristotle was already talking about the idea of the whole is something over and above its parts, and not just the sum of them all. You can find that in Aristotle. Now, Aristotle wrote a lot, and so maybe you find a lot of different things in his writing. But the point here is that he must have realized that interactions of parts and their non-linearity, that was, of course, not a term that he probably could use, are important for something to become a whole. The next person I would like to cite, and that's also really influenced by Stu Kaufmann, is Kant, who coined the term organization, organism actually, organism for a living entity. An organized product of nature is that in which all has purpose and is conversely a means. It's kind of typically Kant, complex. I read Kant in German, and I found that it's much better to read him in a translation, because the translator has really gone to a long effort to make it more understandable. So, Kant paraphrased by Stu Kaufmann, the whole exists for and by means of the parts, and the parts exist for and by means of the whole. Really strange kind of circular relationship between cause and effect of things. And then I want to cite, at least briefly, the famous British emergentists. Those were natural philosophers in the 19th century that realized that in chemistry, something strange is going on as compared to physics. There are new things coming, or new properties of things coming into being if you have reactions, chemical reactions. Through these reactions, apparently, new things things with new properties can be created that weren't there in the elements that came together. And so, for example, John Stuart Mill and George Henry Lewis talked about this, that there might be other kinds of causes than the causes that physics considers. And the main point here was that I think they realized that novelty, these new properties, are emergent. They're coming through the interaction of these elements. Water is a paradigmatic example. You have hydrogen, you have oxygen, put them together into water by violent reaction, and you get all kinds of properties of this new matter that hasn't been there in the parts. It has to do with the bonds, of course, but it's a very interesting type of thing, and it connects emergence to chemistry in some sense, at least early on. Let me give you a few examples of the evidence of properties, emergent properties of systems. For example, the stability of an atomic nucleus, or the solidity of a body. Now, these are all terms that we use in physics. The synchrony of a neural assembly may be closer to AI or biological eye. The efficiency of an algorithm, and the cohesion of a family, a more social concept, and the consistency of a theory. All of these terms are actually describing emergent properties of these things. They cannot be assigned to parts. For example, the efficiency of an algorithm cannot be assigned to part of the algorithm. It's the total collaboration of all its parts, all its instructions that make it possible to determine the efficiency of an algorithm. So there's plenty of hints that emergence is there in many systems. And so my thinking was, is there sort of a playground, a formal playground in which we can see that at work on a level that we can wrap our head around, actually. And I'm a physicist originally by training, but I'm using the computer a lot, and I need the computer to understand things. So I play with little models that maybe can capture a few of the features of the world. So let me talk a bit more about artificial chemistry. It's actually an abstraction of real chemistry. So don't expect it to be a model of chemistry, a real model in the sense that it is very close to the real chemistry. In fact, the strength of artificial chemistries is that it gives you freedom to abstract away what you think is not important for your particular purpose of modeling or understanding. There are a few terms. The atoms and molecules become objects or agents in artificial chemistries. Reactions and bonding become interactions. And the reaction vessel and the dynamical process of reactions in collectives becomes an algorithmic process. You set this up in a computer. You don't have to set it up in a computer, but that's the main thing I use. And what do we get? We get nonlinear dynamic interactions unfolding over time through the execution of this algorithmic process. We occasionally find new objects if we set it up, the rules of the interactions properly. We find new objects in those systems. And we also discover or observe so-called circular production or circular causation, which from a logic point of view was what I already talked about with citing Kant, a bit of a conundrum. Circular production of things. Now, just to give you a few examples, for example, symbols could be the objects, numbers could be objects, strings could be objects, lambda expressions, that has been a famous system of artificial chemistry, binary strings, that's what I used, proof statements, abstract data structures, and then also physical devices like magnets or actual molecules that are set up in a way that their interaction is programmable. All of those can be objects of artificial chemistries. Then you have the reactions. You might have just tables of interaction where you write down all the objects and in a table and note their interactions. That's an explicit way of doing it. It's a bit tedious. You could have string matching rules, lambda calculus operations, arithmetic operations, electronic hardware operations of other types, term substitutions, finite automata transition rules, Turing machine operations, and on it goes. The dynamics can be done by explicit simulation of the objects and their interaction, but you can also try to model it by differential equations that, however, then need to be integrated to observe the development of the dynamics, and this integration is, in most cases, not possible analytically. It has to be simulated, it has to be numerically integrated. And you can also have mixed processes. More formally, so we have an artificial chemistry defined as a tuple of objects, a set of objects. Actually, it's a multi-set of objects, really. But let's talk about that later. It's a set of objects, a set of reaction rules, interaction rules, and an algorithm that executes this and implements the dynamics. And for example, these objects or molecules could be called S1 to Sn, and then you have reactions, just a set of reactions, each one of a particular type that defines how these objects can interact with each other. And here are 4 types of them. It's possible actually to have more different types. Let me give you an example to walk you through this. Here's what I found 30 years ago. It's the so-called matrix chemistry. It consists of bit strings, and here they are in a plate, bit strings in a plate, these wiggly things. And occasionally what happens is that one of these bit strings becomes an operator by folding into a 2-dimensional structure. And this is an operator, this is a matrix now. And it can interact with bit strings in a particular way that we define as the matrix multiplication. It's a mathematical, simple mathematical operation. And then you watch a system of those bit strings with the property that they can fold into matrices and act on other bit strings, and watch what happens in such a system. And the interesting thing that happens, or maybe not so unsurprising, is that, first of all, if they interact, they will produce another string, right? A matrix multiplication of a matrix with a string will produce a new string. So we have this problem of a growing population, if you want this to call a population. What we do is we keep the population constant by just taking out one of the strings randomly. And what then happens is that very quickly replicating and self-replicating bit strings pop up and multiply, because those are the ones that have the best chance to reproduce in such a system. I'll talk about that a bit. So this is the matrix multiplication. If you have just such a primitive system, you see here, this is bit strings, random bit strings actually that are thrown into this plate, and now we select, just go through one reaction. We select two, we fold one into a matrix, and we let it react. It produces another string. That string is put into the population, and then another string is removed. So, very easy. And we take m of these steps, if you have m being the population size, to get a generation. Here's the algorithm. What happens? So, as I said, here's just a concentration looking at a very primitive system of only strings of 4 bits. So 4 bits, very primitive. What we see here is that we start out with two individual strings in high concentration, and nobody else is on the plate. And through the interaction, very quickly, some other strings show up and pop up and populate and push out the original strings. So this is like something was there in the beginning, it interacted, and suddenly it's pushed out and something else shows up. And that something else is an organization. It's something that has the following features. If you look at the reaction graph in this system, you see that there are a self-replicating and replicating strings in this. And they support each other, and because of their support to each other, they are able to push out everybody else from this little world. Okay, so this was a very primitive example. It was bit strings of length 4, not very much really to talk about. There are just 16 examples, different types. But what you can already see here is that, for example, what emerged here is a kind of ecosystem in the sense that there are some string types supporting each other. They're not pushing for themselves, they're supporting others. So if you look at the combinatorics of such systems with strings of 4 bits, you have just 16 different types, but you have already a huge number of reactions possible. If you go to 10 bits or 100 bits, it's astronomical. So this is a really combinatorial explosion of a system, and it's just one example of artificial chemistry. They are much more complex now today, but there are a couple of terms that are perhaps useful to understand. One is that the differentiation between implicit artificial chemistries, where the interaction between the molecules is calculated at the time of interaction. So you just watch it and then you calculate based on the rule of interaction. That's what we did in this example before. But you can also do it explicitly by noting down the interactions, and that's what most of chemistry does. There's still some interactions or reactions in chemistry that are unknown, and they're added to the list of reactions. But in these kind of systems, you can also have explicit artificial chemistries where you write down the reactions from the get-go. And one is the so-called chameleon puzzle, where the idea is you have chameleons encountering each other and then changing their color based on whom they encounter. So this is you can write this down in a table, in a reaction list, and also in differential equations. That's another one of those things. In our case of the very short bit string matrix chemistry, you can also write it down in tables and so on and formally look at that. Okay, so if we, for example, here, I'll jump over this. Here's an example where this chemistry can then be written down as a differential equation, ordinary differential equations, and then that can be solved. And for large number of molecules or objects, it's actually approaching, not surprisingly, this more exact description for the approximation to infinity. Okay, there are two other terms, so implicit versus explicit, and the other two are constructive versus non-constructive artificial chemistries, and the non-constructive ones are kind of less interesting. You have already all the players, the objects, and you just watch their interactions and the collective phenomena that show up from the interaction. The constructive ones are where new species of objects are being created in the course of the execution of interactions. And we can do that in the matrix chemistries as well. It gets a bit wiggly, but you can actually see new species here regularly showing up. I have to jump over this example because of interest of time. That's another example of artificial chemistry. So let me connect this to maybe to genetic algorithms for a moment, or to artificial life. But it's interesting. What we have is we have a system that has, based on the interactions, the ability to develop over time, and then you can, in hindsight, so to speak, you can assign fitness to certain types of objects, because certain types of objects will be dominating over the longer term. So you can assign a fitness, but it's like in biology, it's a post hoc fitness. It's not a fitness that we assign right away from the get-go. It's a consequence of the interactions. It's not being programmed into the system. But you can make an attempt, so it has its own internal agenda. It's a bit like life is. This bubbles, and it does things that are out of your hand if you run the execution of these algorithms, because it's set by the interactions that you put in. So, but we can influence that externally by adding some kind of device that picks out strings occasionally and looks at them from another point of view. For example, this is a bit string in the example of bit string chemistries. You can assign a quality to each of these bit strings if you want, that has nothing to do with the internals of this plate of multiplication, but has to do maybe with the information that that bit string carries. Suppose it's something you're interested in, a particular bit string pattern that is a solution to your problem. It could be an optimization problem. You can assign a quality to each of these strings and then say, occasionally I kick out one that I don't like, or kick out one. I let the system do the replication, and I, from the outside, intervene by destroying certain ones that I feel bad. Now you can do that. It's interesting, but what these kind of systems do is, if you are not careful enough, then you destroy the dynamics. You have to be very careful. If you do a soft pressure into the direction of your external fitness function that you have through the quality of each of these strings from the outside, judging them from the outside, you can actually get the system evolving into the direction you wish. But if you push too much, it breaks down. The dynamics breaks down. I think that's a very interesting thing. It's as if we also have to be careful what we do in our world and how much we push other living organisms, not to overdo the pressure on them and kill the certain subsystems of the ecosystem. Okay. I think ACs, artificial chemistries, can be considered a spin-off from artificial life. life as it could be, is the Langton motto. ACHEM, artificial chemistry, chemical reactions as they could be imagined. So there's this freedom now. You can really set up even mathematical interactions. Of course, you can become more serious and do something that is closer to chemistry. But the idea here is we have tools that hopefully helps us approach or wrap our head around understanding phenomena of emergence. And if you argue, actually, I came to this field caused by the question some people posed, I think, in the 90s already, and well, I later interpreted this way. What is the right stuff to implement life, or to try to get to life in the artificial life sense? And I was thinking, okay, if we look at real life, the basics of real life are chemistry. So maybe if we want artificial life, we have to do something that is also more basic, and that is then what we formulated as artificial chemistries. There are different forms of them now. There's lots of work going on that you could see from this point of view. DNA computing, for example, is a typical type of wet artificial chemistry where you set up the interactions in a way that computing can be done with it. Reaction, this is all in the area of computing. Reaction diffusion computing. But I would also count protocells in the artificial chemistry area, in the wet artificial chemistry area. You play with the interactions and you set them up in a proper way so that, in this case, maybe cells form. And you can do computing with bacteria and slime molds and all that kind of small organisms. And for example, here is bacterial computing of the Hamiltonian path optimization problem being implemented. That is sort of informing, here's the computing is informing us about how to do this, setting up the system in such a way. But then there's lots of in silico artificial chemistries that use that. And, you know, the abstractions of chemistry provide an interesting point of view also for other sciences. For example, in nuclear physics, we have a lot of reactions. In this case, it's the reactions of nuclei. Even in elementary particle physics. Oh, okay. Yes, okay. Is that better? Sorry about it. Yeah, I'm okay. I don't feel threatened by the mic. Communication by language, music, and economies all have an aspect of interacting objects that can be coached in terms of an artificial chemistry and at least can be looked at from this perspective. And it's a different perspective from the typical one that people take. On music, for example, I should explain this. The interaction of the sounds that make you perceive a particular piece as harmony, the interaction of the notes. You could look at that from the point of view of the interaction of sounds, and that can be sort of coached as an artificial chemistry. There's actually artificial chemistries that produce music. I have an example on this computer, but I don't play that and have not time for that right now. But it's interesting that you can also do this on the level of musical notes. Economies, I will talk about that later. How much time do I have? Okay. We have about 10 minutes, or? Okay. Okay, there are different approaches to artificial chemistries. Rewriting systems is one class. Rewriting systems take a piece of symbols, a sequence of symbols, and have set rules, the rewriting rules, to produce a new sentence, let's say, in a particular language. Lambda calculus is one. There are other systems of this type. And all of this is discussed in our book in detail. So if you're interested, you can look at that in details. Automata and machines can be considered as artificial chemistries, have been used to implement artificial chemistries. Famous ones are the Tierra, Avida, and Amoeba system. The core world could be also considered an artificial chemistry. And then there are bio-inspired ones that are more complex, string-based bio-inspired ones like Susan Stepney's, string mole, lock and key, artificial chemistries, swarms. There are many examples. And so today, many people play with these systems, and I think quite a few of them claim those are artificial chemistries, and I tend to agree this is indeed conceptually fits in. Okay, this was a rough thing about maybe I should jump over the organizations and talk about the play I made over the pandemic, because 10 minutes it's enough only enough to do one. So this is a formal thing about organizations. We have talked about Maturana and Varela, and what self-maintenance and closed systems are an important thing. We have also worked on this. Let me jump over this and go to social economic modeling for a moment. When the pandemic hit, I was thinking, oh, I'm stuck at home now for I don't know how long. Time to do something that I always wanted to do and had no time to do. And so this is the result of it. It has to do with the problem of inequality in society. And as we know, and this is just an example from the United States, wealth is heavily unequally distributed in our societies. Here, the upper green is just the percentage of wealth in the United States and the development over time from 1990 to 2020 for the last 1%. When you see here 90 to 99%, that's below, and the upper green is all owned by the last one, the highest 1%. It's an extreme development. It was bad enough in 1990, it's terrible in 2020, and there seems no end in sight to the development of inequality. Now, historians have talked a long time about the danger of economic inequality being a strong contributor to societal collapse. Unrest, for example, unhealthy populations. I mean, it has an impact on population health, and it can produce environmental catastrophes. So there are these people, historians, that it's maybe something that has to do with catastrophic events in society that actually sometimes help to rectify those things. And we don't want these catastrophes to rectify social inequalities. We want to be a bit more clever about it, rather than having wars or pandemics or something like that. do it. And if you look closer, and that's where the physicists come in, here's adjusted gross income, and that's the United States. You see that the adjusted gross income statistically follows Boltzmann-Gibbs distribution. And the same is true for wealth. It also follows a Boltzmann-Gibbs distribution with a tail, a so-called Pareto tail. It's very interesting. It seems to be a universal phenomenon that these kind of distributions pop up. Why is that? There's an entire field now called econophysics, where people think about this and bring in the tools of physics, thermodynamics and others, to discuss the statistical effects of wealth development. And there's a book, for example, from Chakrabarty. It seems that these observed regularities in income distribution may indicate a natural law of economics. Mandelbrot, Benoit, the famous one for fractals, he, in 1960, in a work, observed that there's a great temptation to consider the exchanges of money which occur in economic interaction, artificial chemistry, you see the connection, as analogous to exchanges of energy which occur in physical shocks between molecules. So he recognized that in 1960. And then the physicists produced a model. It's the so-called kinetic exchange model of economic activity, in which they talk about money exchange between agents as the process by which wealth distribution develops over time. And they talk about it in terms of energy. So here's the idea of these kinetic models. I criticize these models, but let me just explain. So you have two players, and they're called M1 and M2, and M is their wealth. And they exchange a bit of their wealth in an economic interaction. That could be an exchange of an object for money. That's somebody sells something to the other guy. We're not looking at at goods here. We are only looking at the money or at the wealth, because the goods might be consumed and disappear from the world. So the idea here is two agents come together, put together their wealth, and then a random proportion of this is distributed to each of the agents. The idea is they put their wealth together, and then a random proportion of it is given to either of them. A different proportion, of course, in most cases, because hitting 0.5 is not very probable. So that's their model. So they have them. Okay, initially, you set up this as a population, and you watch what happens if you have this primitive process of interaction in an economic model. And every so often, two random agents meet and exchange a random amount of money based on the proportion of their joint wealth, That's the idea of the econophysicists, which is typical for an energy model. The problem with it is it's not realistic for economy, but it is at least an idea. So yeah, everybody gets a different amount. And now the interesting thing, if you watch that over time, what happens is it produces these terrible unequal distributions of wealth in those economies. How? The richer get rich by these interactions, and the poorer get poorer. And over time, you have an exponential distribution of wealth. You do nothing else than just say it's a random amount of money that exchanges. They start out all equal at the beginning, and you still end up with this. So that's this intuition. Maybe there's a very strong natural tendency of economic exchanges to lead to inequality. And so my idea was, well, if that's the case, maybe we have to look very seriously at taxing wealth as a solution to this problem. And if we understand and recognize that it's the natural outcome of systems of economic interactions, even if they are totally primitively modeled, which means it's very general to all kinds of interactions in economy, to all kinds of economic systems. If that is the general tendency, we have to, once we recognize it, we have to counteract this if we want to avoid inequality. Now, I guess we are all agreeable that we want to push away from inequality because of the danger to humanity about it. How to do this? So what I did was I played with a couple of these models that are now based on another assumption. The assumption here is that the poorer agent determines the maximum of the exchange, which is probably more real than it's not anymore an energy now. It cannot be coached in terms of energy because it doesn't put together both of these strengths and averages it out. So it's based on the minimum, and then I'll set up an artificial chemistry to do that and look at it again. It's even worse in terms of the interaction and production of inequality in society. So it's in all of these systems, it happens that inequality develops. And to compensate for that, we have to, that's the lesson I learned, we have to encourage taxes on wealth, because while our existing welfare system attempts to stem these forces, it's not at all effective at it. And just to remember people, I think taxation and government has come into a bad reputation, tax in general, because it's considered as a grab of the government for the money of people. But there are different roles for taxes in society. 3 different roles I see. One is to generate income for the government, to produce infrastructure for all society, and that's a legitimate one, but it's one that is in dispute, unfortunately. The second role is to redistribute the wealth between segments of society, and that's, I think, an important role that hasn't been emphasized enough. We have to, government is probably the only way to do this unless we want war or diseases take care of this. Because we know that in pandemics, the inequality was also sort of dampened. And the final one is to discourage certain behaviors of individuals. That's also a role of taxes, like cigarette taxes or alcohol taxes and so on. And that's a different role of taxes. I only want to look at the redistributive effects. And I did this simulation on taxation, putting taxation on this very primitive economic model. And what I see is if take, for example, a flat income tax of 30% for everybody. Flat income taxes are the thing that some of the conservative politicians nowadays advertise. If you look at the time development of this, you see it doesn't help. The 1%, 10%, always upper 1% or 10% always gain from this. This is, by the way, without taxes, and even with high progressive income taxes, not flat tax. Progressive income tax is not a big help in this. However, if I put in a wealth tax, I can stabilize in these primitive economic systems, I can stabilize the distribution in the middle. And that's the only way to do it. I was a bit surprised by this result, but if you start thinking about it, income taxes, the dampening of the inequality of income, can only determine something about the future. And apparently it's even for the future ineffective. Wealth tax is the only way that addresses the current inequality that already exists. Without a wealth tax, you can't do that. And so I stop very soon. This is the lesson that I took from this. It's maybe a very simple-minded lesson, but I think it's probably the only solution to our inequality problem, to have a serious wealth tax. Now, I'm glad to report that Thomas Piketty is of the same opinion. He has just published a new book on the history of equality in society. It's actually a positive book where he talks about that in the history of humanity, actually there was a march towards equality, but it has stopped for many years now, for decades. And if we want to increase equality again in society, this is the way to go. Okay, let me jump over this. Also over the critique, you can of course critique this. You can say, what about avoidance of taxes and so on and so forth? Yes, all of this has to be addressed. I've published this in +1, if you want to know more. All of this has to be addressed, but at the level of these models, these models are too simple to actually look at tax avoidance and this kind of more complications. That's, of course, something that has to be addressed, but I'm not thinking that it can be addressed right away in these kind of systems unless we make them more complicated. So, step back for a moment. In this talk, we have seen that many different artificial chemistries, at least the potential for them. They're agent-based systems with simple agents. They're really simple agents. The interactions are then lead to emergent phenomena. These have their own agenda that could be called implicit fitness. And from many complex systems, you can derive these artificial chemistries. So there are ways to formalize toy systems at this point, but maybe there's something in this as well that is more serious about how the progress of science has to go, because it seems to me that with the advent of the computer and the simulation, we have such a new world opened up to us that's not mathematical, that's algorithmic, and probably our world and the models of complex systems for our world can only be seriously addressed by using such kinds of tools. And because it requires simulation, these systems require simulations. We are not in the world of eternal truth. In a world of events and processes we are, where novelty creation is standard and happens a lot. And we have to come to terms with this, and our current mathematical formalisms cannot do this. Now, it's powerful. Mathematics is powerful in its own realm. Physics is powerful in its own realm, but these disciplines have excluded certain things that they can't treat, yet they are present in the world, and we have to develop tools for them to address them and understand them and maybe model them, predict them, and in the future benefit from this knowledge. And here I end. Thank you very much.
Okay. So, other questions?
So thank you. You know, as for the last things, I'm sure that you know that there are many activities that I could direct you to some colleagues that can tell you a lot about this. I wanted to instead give another perspective for this general framework, and the perspective, or try to give a perspective, is in astrobiology. Mm-hmm. So as you know, life as we know it is based on two things: carbon-based chemistry and water as a solvent. Yeah. And of course, this is the result of one possible pathways out of zillions of possibilities. And the question is, elsewhere in the universe, there can be life in a different form with a different chemistry, different biologies. So I was wondering whether this framework, this arsenal technique that you have set up, can give boundaries to the possibilities that, of course, are universally large. Whether some are possible and some are not. We can rule out some of the possibilities.
Okay, astrobiology. So you would have to. I don't think. Well, okay. There are people looking at astrobiological applications of artificial chemistries. Yes, there are. Now, I think they are not looking at constraints yet. They're looking at possibilities rather than constraints, or probable possibilities, things that are more likely than others. But I think having constraints is more powerful than that. And it might be possible. I haven't thought about it, but that's actually a good suggestion, to look at the constraints of possibilities. Because if you have constraints, you exclude certain classes of things. It's much more powerful than just showing in an example that this might happen. Thank you. Good point.
Okay, Anata, you. Thank you for your very inspiring talk. I have a lot of questions, only one, on the part of the artificial chemistry and emergence. Sometimes I have to think about emergence. Emergence probably is, in a part, in the area of the observer. We are identifying some new object or collection. So I wish a comment of you. Have you ever observed a new kind of object in your artificial chemistry, and in which way can you identify new kind of object that was not planned? And one of my talks is about causally convincing object. So collection, new kind of structure that can cause event, and we could observe a chain of causation. But it is, again, a question about the emergence of a new level.
Yes.
Probably. Lot of things. I wish some comment. Thank you.
So the first question, very often novelty is in the eye of the observer. So it's a surprise thing for a person, for an observer, but it's actually not new. It's just this person wasn't informed about the novelty of this existing already in the world, and they're surprised and say, "Oh, this is emergent," but it isn't emergent because it was there already. I mean, not strong emergent. It's not really new. It was there before, but somebody didn't know about it. So yeah. I'm a sort of a believer in this strong emergence hypothesis, that actually new things, really that it happens. But we have to be careful about the conceptual difference between epistemological, about knowledge emergence, and the actual real emergence that happens in systems, ontological emergence. But it brings in the observer, and the observer is an important part of it, because if I don't know what is new, or I have to have some measure of newness to be able to say that something is new or not. And I think it's not a solved problem. This is an important question. How can we sort of have model the observer with the system so that we have the observer as part of the concept of emergence? I don't have an answer to that question. It's a difficult one. Now, the second point you mentioned, could you recall me, remember me? What was the second point? Your second point? What was your second point?
I don't remember. It is a very complex and complicated question. Something about the emergence of a new level. If
emergence of new levels.
Observe something similar, but I don't pretend an answer.
Yeah.
I think it is a.
This is a very difficult.
I wish some comment because you are.
Oh, okay. Yeah. So what is certainly clear is it happens it doesn't happen as often. The emergence of new levels don't happen as often as these smaller kinds of novelties and so on. But they apparently have happened in the history of the universe, and maybe they will happen again in transition of a society to something more, I don't know, more cohesive. I don't know. But yeah, it's not happening very often, and therefore it's a process that is difficult to examine because it's so seldomly happening. Yeah.
I will limit myself to one.
Yes.
Yeah, it was a very interesting talk. Regarding to your simulation about inequality, one thing that I find is often missing is the discussion of ergodicity, meaning that if you have wealth inequality, which is static, but if people can move very quickly from one position to the other, then that would make it maybe less problematic, meaning that, for example, if you're rich and I'm poor, that's not fun for me, but if I know that if I wait a bit, then our roles are reversed, then it might not be that bad. And is this not something that your toy model would predict, that the rich are very rich, but they're not rich very long, and everyone who is poor is at some point they're relatively rich?
Let's see. I think I haven't looked at that. My intuition about it is that this exchange of agents, I have to look at this in more detail. Probably we should talk about it after the session. It's an interesting question you have, and I'm certainly happy to think about it in more detail. I don't have an answer right now. Sorry.
Okay, it's more a comment than a question. I mean, you raised a huge number of arguments, so I keep many questions aside. I don't enter into the social or economic model, but rather, I really liked your excursus on emergence. So this part was really interesting. Also, the part on artificial chemistries, when new things come into play. We have been playing with Marco, with the binary polymer model, and these things happen. I think there will be a talk on this model later. But, well, one comment, it has to do with emergence and with one of your slides. At a certain time, you mentioned protocells.
Yes.
Protocells do not come out of playing with molecules. They are not there. I mean, you can have these systems and they generate lipids and so on and so forth. But the fact that lipids make vesicles, and vesicles are the container which allows to distinguish an interior from an exterior, does not come from those equations. So this may have to deal with the matter of levels. I mean, in that case, emergence comes from elsewhere.
Yes. To my knowledge, I thought that lipids can spontaneously form vesicles.
This is also true.
And therefore, if you have a mix of...
In any case, this comes from outside. It's not from the equations. I find that in many works on the origin of life or similar things, there is an overemphasis on chemical reactions.
Mm-hmm.
They make this collectively autocatalytic sets, which you showed without calling them like that. But this is not the whole story. I mean, there are other parts from probably physics and other things which are key to the process.
Right. So I guess I should drop this from the list of artificial chemistries here.
No, please don't do it. Please handle the issue of emergence in that case.
Okay. Well, thank you very much.
So thank you again. I think there would have been more questions, but there is not time. We can go on during the coffee break and so on.